Hi, and welcome to my second Devlog episode. In the last episode, I showed you how I implemented a very simple soft body cube by simulating point masses with distance constraints. The problem with this approach is that the cube doesn't preserve its shape when it gets too soft. It just flattens on the ground. So this time I will show you how adding a global volume constraint can help with that. The volume constraint also allows me to pump up the Stanford Bunny and make it explode. Before diving into the fun constraint math, I wanted to make the scene more interactive. Previously, the only thing I could do was press R to reset the cube, which gets a bit boring. The first thing I did was to make the cube grabbable. My idea here was to grab a single triangle and make the initially grabbed position follow the position of the mouse. However, because the body is soft, it is unclear where this position actually is in the future. So instead I compute the distances of each triangle corner to the grabbed position and then use stiff distance constraints to keep these distances to the future mouse positions. This approach also allows the triangle to dangle around the mouse position. The implementation involves a few different steps. To compute the grabbed point, I shot a mouse ray through the scene and checked for each triangle if and where it hits. For a triangle T with the corners A, B and C, and a given ray R that starts in S and shoots in the positive direction of D, the hit point can be computed by intersecting the ray with the plane PT the triangle lies in. A plane can be defined by a base point and a normal vector. Here I chose A as the base of the plane and N as the normal vector, which can be computed by taking the cross product of two triangle edge vectors. Every point X that lies on the plane is perpendicular to N when looking at it relative to A. This is why the dot product, which is denoted by this superscript capital T, must be 0. Intersecting the ray R with the plane is as simple as inserting its equation into the equation of the plane. With some reordering, the ray parameter T of the intersection can be computed. Inserting this T into the ray equation gives the hit point. Contrary to the infinite plane, the triangle is bounded by its edges. So now I need to check whether the hit point actually lies inside of the triangle. For each edge vector, I check whether the point lies to the left of it. Here the cross product helps again, this time with its anti-commutative property. If the point lies to the left of the edge vector, the cross product points in the same direction as the normal vector. So for each edge vector, I check if the dot product of the normal vector and the cross product is greater than 0. If the point would lie outside of the triangle, as you can see here, the cross product would point in the opposite direction. However, if the winding order of the triangle is not like in this setup, it is important to check the exact opposite case. Then the point would lie to the right of every edge vector. So if all cross products point in the opposite normal direction, there is still an intersection. That's how I tested a given ray for an intersection with the triangle. To construct the ray itself, it helps to remember how the transformation pipeline for rendering works. In order to render any object in OpenGL, it must be transformed into this cube with side length 2 lying in the origin. The coordinate space of the cube is called normalized device coordinates. Everything outside of this cube will not appear on your screen. As you can see here, not every part of the ground plane is rendered, because it's not inside of the cube. The world space where all objects sit in must be transformed into these normalized device coordinates by applying a view and a projection transformation. The view transformation basically says where the camera is located in the world. Multiplying a point with the view matrix transforms it so that the original view frame is now in the origin. The projection transformation then defines a frustum, which is converted into the normalized device coordinate cube. The final step is to convert the normalized device coordinates to pixel coordinates. This is done by a viewport transformation, which you can describe in OpenGL with the GL_viewport function. It scales the x and y position of each point by half the screen size and does some moving. Now, to convert the mouse click position into a ray in world coordinates, we need to reverse this process. First, the 2D mouse position is converted into a corresponding xy position in normalized device coordinates. This 2D position can be used at the near and far ends of the cube to get the 2 points that define the mouse ray. To get the ray world coordinates, I apply the inverse projection and view matrix to both of these points. And that's the mouse ray. For each triangle, I test for an intersection. To compute the grabbing positions of the following frames, I intersect the new ray with the plane that is described by the starting grab position and the view direction as the normal direction. While simulating, the 3 points are constrained with 3 distance constraints to the mouse position. Now I can move the object around with my mouse. Another thing that got a bit annoying was trying out different program parameters like the spring's inverse stiffness or the simulation's time step delta t. I had to edit the code, recompile and rerun every time. To make it easier, I added the dear ImGUI library as a submodule to my Git project. Compiling the library was as simple as putting this into my build lib script. The resulting .a file could then be used to link the library against my program with the addition of the correct include path and a C++11 flag. I used this example to get the basic setup working. First, I included the ImGUI backends that correspond to the SDL library and the OpenGL API I used. Then I initialized ImGUI and its backends by passing contexts and versions around. Drawing is done by requesting a new frame, actually building the interface like this cool demo window here, and finally letting ImGUI render it. Because a GUI doesn't work without user input, every event generated by SDL needs to be passed to ImGUI too. Now the ImGUI demo window gets drawn. Though as you can see, there is no differentiation between the events that belong to ImGUI and the ones that should be passed to my game. Fixing this is made possible by asking ImGUI if it claimed an event and then not processing it myself. For example, mouse events can be checked like this. Creating a slider is as simple as beginning your own window and calling the slider function where the variable in question will be modified immediately. Except for the fact that ImGUI doesn't support doubles as inputs. But after writing a custom function for that and adding some text, I could finally modify the stiffness of the cube while the program is running.
Now fixing this problem. The idea is to constrain the volume of the cube to its initial volume such that it at least can't flatten anymore. So the formulation of the constraint looks like this. V is the current volume of the mesh and V0 its initial volume. If this expression gets 0, the current volume equals the initial volume, which is what we wanted. To compute the volume of the mesh, there is a really simple and elegant way to do it. Maybe you remember the scalar triple product from linear algebra. Given three vectors a, b, and c, it computes the signed volume of the parallelepiped that is defined by these vectors. Signed means that the expression can be positive or negative, depending on the order of the vectors. In this setup, the signed volume is positive. But if the vectors are swapped like this, for example, the signed volume becomes negative. Suppose the vectors a, b, and c now represent the triangle of our mesh. The enclosed 3D object below that triangle is a tetrahedron. Can you imagine that it actually fits 6 times into the parallelepiped? This is why its volume can be computed just by dividing the volume of the parallelepiped by 6. This relation can be used to compute the volume of an entire mesh. Let's consider this torus as an example. Regardless of where the origin lies, the volume of the torus mesh can be computed by summing the signed volumes of all tetrahedrals that are formed by the triangles and the origin. So here I is the index of the triangle and Ti0, Ti1 and Ti2 represent the position indices of the 3 triangle corners. The indices are used to obtain the actual corner positions of the triangle, Pti0, Pti1 and Pti2. There are nt triangles, so nt-1 is the last triangle index. The formula makes use of the signedness of the tetrahedral volumes. If the torus has a consistent triangle winding order, which it most likely does because it's used for rendering, then these triangles produce a positive volume. These triangles produce a negative volume because they are facing the other way. The same happens for the other part of the torus. The signed volumes cancel each other out where there is no torus and only the actual torus remains. I think this is really cool. For this method to work, the mesh needs to be properly closed and have a consistent and correct triangle winding order, like I said. The volume constraint can be rewritten to this. For each triangle, there's an addend in our sum. If you remember my custom constraint summary from the last episode, the constraint needs to be derived with respect to every position that is part of the expression, which is every position of the mesh. Although it might look a bit rough, it's actually not super complicated. The most important difference from your differential calculus class in high school is that there are more variables involved, which is also why this weird symbol instead of a simple d is used. Also, it's not possible to use rules like the product rule for single variable derivatives directly, because unlike with scalar values, when dealing with matrices, the order of multiplication is important.
Luckily, the Jacobian matrix always tells us how to break these expressions down, so that the derivation rules for single variables can be used again. For example, suppose we have a function a that takes a 3D vector x as its input and produces a 3D vector as its output. Deriving with respect to x looks like this. Each row corresponds to the same output row of the a function. Each column, the expression is derived with respect to a different entry of x. As you can see, the matrix only consists of scalar-valued variables, and it's possible to use the corresponding derivation rules again. Let's use the Jacobian matrix to derive the rule for the dot product. For this, we need two vector functions instead of just one. Here I use a and b. The dot product is defined like this. For readability, I will drop the dependence of x. The expression can be rewritten using sum notation. With that, the derivative can be rewritten too. Because the dot product only produces a single value, there exists only one row in the Jacobian matrix. Each column, the dot product is derived with respect to a different entry of x. Taking the derivative of a variable is a linear operation, meaning it can be distributed over sums. Now there are only simple single-valued derivatives again. The product rule can be applied. Next, the matrix is split up into two parts. The goal here is to simplify the expression to use matrix multiplications. Let's have a look at the first entry of the left matrix. Written out, we can see it's actually the dot product between b and the vector a derived by x0. There are two ways to express this. However, the right one makes it easier to simplify the expression in further steps. Looking at the other entries, they are all like this, so let's rewrite all of them. Thinking about this for a bit, each entry just multiplies a row with a column. So it's possible to place b and a outside of the matrices to form a matrix multiplication. The two matrices are now exactly the definition of the Jacobian matrix of a and b. So the expression can be simplified further to finally get the dot product derivation rule. While it might look like the product rule for single variable derivatives, it's important to understand that reordering the terms is not necessarily correct. For example, the first two aren't even valid math syntax, and the last one is wrong too because it produces a different result. This is crucial to understand when deriving more complex functions. The last rule that is needed to derive the volume constraint is the one for the cross product. Again, given the same vector functions a and b, the cross product is defined like this. Dropping the dependence of x for readability leaves this. The derivation is a little bit more involved, so I'm just going to give the result. The derivative can be simplified to this expression, where the superscript x denotes the cross product matrix you can see here. Given the result, you can try to derive the expression yourself. If you want, I can help in the comments. Using the dot and cross product rules now make it relatively easy to derive the volume constraint. V0 drops because it is a constant, and the derivation operation can be distributed over the sum again. First, the dot product rule is applied, followed by the rule for the cross product. Because matrix multiplication is distributive over sums, this factor can be applied to the two matrices inside the parentheses. Multiplying a vector with a cross product matrix like this can be simplified to just taking the cross product of the two vectors like this. Again, I want to note that the details here are extremely important. Without transposing the cross product column vector, the expression would be invalid. Even worse, in other cases, the multiplication might still be valid but produce a wrong result unnoticed. Using the anti-commutative property of the cross product again, the two terms here can be reordered to get rid of the minus. Finally, let's reorder the summons such that the index of the derived vector is in increasing order. That's it. To remove the remaining derivatives, x can be replaced by the actual variable vectors. Matching vectors produce the identity matrix, and otherwise the result is the zero matrix, greatly simplifying the expressions. Finally, the volume constraint can be implemented. The function that solves the constraint takes the mesh positions x, their inverse masses w, the number of positions count, a buffer jj that stores the derivative vectors for every position, a list of triangles with the corresponding count, the current volume of the mesh v, the initial volume v0, and finally the lambda variable and the modified inverse stiffness of the constraint like I explained last episode. First, the constraint value cj is computed. If the value is 0, the constraint doesn't need to be solved, so this is checked here. Next, jj is cleared because the following loop sums up the derived force directions in it. The volume constraint produces possible forces for each point, which is why the size of jj is equal to the number of points. Because of how the constraint is formulated, these force directions can only be obtained by looking at the triangles. So this is why I need to iterate over the triangles and add the force directions for each point into jj. I0, I1 and I2 are the position indices of the triangle corners. P0, P1 and P2 are the actual respective positions. What follows is the computation of the denominator for the delta lambda variable. It can't be simplified like the distance constraint, so the loop and jj is needed. Finally, each point can be corrected and lambda can be updated. Solving this constraint once in the solver loop, like I explained last episode, it creates a pyramid cube. Though it's much more interesting to look at more complex models now that they don't just fall into themselves. Like this ball, for example. I think it looks a bit like there's water inside of it. The mesh doesn't have to be convex though. It can also have concave parts, like this Stanford Bunny. The simulation is quite stable, which is really nice. Interestingly, if only the volume constraints are simulated, we can see that it really just moves the point in any direction that makes the volume be the initial volume. The shape of the mesh is kept approximately by the distance constraints. One small extension to the constraint that can be done is mimicking pressure inside of the mesh. Just add the positive pressure factor to the initial volume of the mesh. This way, the extended position-based dynamics algorithm tries to make the model have a different volume than it actually had initially. So in a sense, p times v0 is the new initial volume of the mesh. If p is set to a value smaller than 1, the model crumples. If p is set to a value greater than 1, the model expands. However, if p becomes too large, the volume and the distance constraints begin to contradict each other. Increasingly stiff distance constraints then make the model begin to rotate, which is really bad. I think this is because the distance constraints are solved in order. If you imagine the distance constraints to be solved along the circular path, it might explain what happens. The volume constraint inflates the mesh extremely, so the first distance constraint has a large error. The corrected points are moved together. The next neighboring constraint now has an even larger error. So the right point moves even further to the left than it would have if the first constraint was not solved. This process continues along the circular path and all points rotate into one direction. I asked what to do about this in the 10-minute physics Discord server by Matthias Müller, one of the authors of the position-based dynamics papers. One member had the idea to solve the constraints in a random order. So I tried that and it got much better. Though sometimes it introduces a little jittering of the positions. Maybe the best solution is to just not increase the artificial pressure too much. Another cool thing that can be done with the extended position-based dynamics method is computing the actual forces the constraints generate. Here is the fundamental equation of motion of the method. As explained last time, the left side represents the internal forces of the system. Lambda is defined like this. Rearranging the equation, we can insert it into the forces equation. Now, for a single distance constraint j, both of the involved points experience the same force, but in opposite directions. To compute the length of this force, we can use that the derivative is a normalized vector. This means the lambda variable can be used to obtain the force of the distance constraint. Using that, for each constraint, I checked if its lambda exceeds a certain value and then marked the edge of that constraint as torn. When rendering, I skipped triangles that have torn edges. Increasing the artificial pressure inside the volume constraint also increases the force of the distance constraints. If that force becomes too large, the edges tear. I can either tear the mesh by moving it fast enough by hand, or I can make it explode by using too much pressure. So this concludes my implementation of the global volume constraint. In the next episode, I will show how I implemented bending constraints to make the model retain its shape even better. Because I ran into some difficulties with this, I will also show how I discovered a different approach to model the mesh that mostly fixes this issue, so I can finally implement a car tire. If you have any questions or feedback, let me know in the comments. I'm happy about any one of them. Thanks for watching.